So class, this is the circuit for lab number 1. We'll be studying the effects of harmonics, as we will do for all the labs, on the utility line side of the load. And in this particular lab, lab 1, we'll study two loads, two switching loads. The first one being a bridge rectifier plus a 57 ohm resistor, a simple circuit. And then we'll replace that 57 ohm load with an inductive load or a non-unity power factor load and check out the harmonics that are generated by that load and how it affects the utility side of that bridge rectifier. I will then store that data in the fluke meter, which consists of the graphs of the voltage, current, and wattage. And we will also store all the data associated with all the harmonics from the fundamental to the 31st. And I will provide that for you at the end of the week. And you will then generate a report for me at the end of the week showing me what you've learned about the effects of harmonics on the line side at the utility based on this particular load. Class, welcome back to Lab 1 for ELEC1631. Now in this lab, as we know, we'll be examining the effects of harmonics on the line side or at the utility side that are generated by a switching load. And the first thing we're going to do here is, for the first part, I'm going to short out the inductor. So we have a pure resistive load here. We're going to turn on the power and check our voltage out on the DC side. It's 90 volts DC, which is what we're after. Okay, so now we're going to swing over here to our Fluke 41B power harmonics analyzer meter and see what it tells us about the harmonics that exist, if any, on the line side or the utility side of that load. So the Fluke 41B is able to show us the voltage, the current, and the wattage, AC of course, for the for this particular load. And we're measuring the voltage, that's our reference, line to neutral, and the current in phase A or the red phase. So here's our voltage as displayed, the voltage waveform. Here's the current waveform. That's our wattage. Back to the voltage. And we see, by looking at both the voltage and the current waveforms, very little distortion. And this is what we expect to see, primarily because the waveform itself, which is a full wave rectified waveform, still is sinusoidal in shape with no distortion to the sinusoid. And you should see very, very little distortion, which seems to be the case here. Now, let's shut off the power, and we're going to pull the short circuit out of the inductor, or across the inductor. And now we have an RL circuit across our bridge rectifier. Let's see what happens now when we turn on the power and 90 volts DC across our load, just as before. And this time, if we go to our Fluke analyzer, we'll see the AC waveform for the voltage still looks like very little distortion, but the current on the line side is severely distorted. In fact, if we want to see how much distortion the current actually is experiencing on the line side, it's actually 31.5% distorted away from a pure sinusoid. Okay, now if we go and look at the harmonic content of the line side current, you can see that all the odd harmonics in this histogram are displayed, and all the harmonics have survived. So that's because this is a 2-pulse rectifier. We'll see in a later lab where we, lab number 2, where we study the 6-pulse rectifier, we're going to actually filter out some of those harmonics and reduce the distortion. So let's now look at the voltage distortion, which is really what we're after here. So we scroll through with our fluke, we retrieve our data, and what you can see there is 2.6% distortion on the line side voltage. Now that doesn't sound like much, but the IEEE 1741 threshold for voltage distortion at a point of common connection, such as a substation, they recommend not to exceed 3% total harmonic distortion on the voltage. And we're getting pretty close there. And the reason it's such a concern is because if we have, say, one rogue customer, if you will, who is generating a lot of harmonics because they actually have a lot of switching loads in their plant, they will be the source of the distortion at the substation. And if we exceed or develop a lot of distortion on the voltage waveform, it will affect the other customers quite possibly. So it behooves that customer who's generating those harmonics to do something about it. And we call that a mitigation technique, which we'll study in lab 5 and 6.